As we try to get application developers onto the FPGA, we knew that VHDL and Verilog were just not going to do it, and OpenCL has yet to play out. What we wanted to do is take their native C code and allow them to just port that directly into an infrastructure that manages their jobs and takes care of data access for them. That's what CAPI Snap is all about. In order for developers to take advantage of our acceleration technology, we've done two things in CAPI Snap. The first is to make a simple API that developers can use to call the accelerated algorithm. The second is make a simple path to take a piece of code that they run today in software and port that over into acceleration.
In a standard server configuration, shown here, the CPU pulls data from storage and the network links and begins operating on that data. The host memory, usually up to 1 terabyte in today's servers, is used to hold hot data that the application is currently using or will soon use. In the case of database analytics, applications retrieve large tables from storage and place these tables in host memory before starting to run query filters to cull that data down to the interesting pieces. This can use an enormous portion of the host memory space. With CAPI, we add an accelerator card to the processing complex. While the CAPI interface communicates directly with the host, the backside of the card can have wide buses to the I/O, in some cases up to 4 times the bandwidth of a PCIe port. Alternatively, the card can house terabytes of flash data, as is the case with our CAPI Flash GT card. So how do these wide connections to the data help with analytics? In the aforementioned database case, we can perform the filter operations on the FPGA, operating an order of magnitude faster while having faster access to the entire database compared to software. With Snap, we add actions to the FPGA. Filtering might be one type of action. After the filtering operation, Snap might store only the interesting data into the host memory, where the application can perform deeper analysis. In the picture, the filtering operation might be action X and would be initiated by the host side application. Our Snap architecture allows for multiple actions, each managed with their own job queue for simultaneous operations. So with CAPI and CAPI Snap, we get the actions acting as threads called by the main application on the host, sharing the same virtual address space. The Snap infrastructure manages the data movement and job controls on behalf of the application after it calls for an accelerated action. So the action need only encompass the data transformation, as the Snap infrastructure manages delivery of the data to the action. The Snap infrastructure and actions all reside on an FPGA card that has direct access to additional storage and resources, as well as the host. Finally, the Vivado toolset assists in creating the FPGA images with the Snap infrastructure. Altogether, this provides the fastest time-to-market data center FPGA platform available, all with the CAPI attributes of virtualization, security, and reliability. It is important to differentiate between development and deployment environments. Development is where we create accelerated IP and integrate it with the target application. Deployment is where end customers use the integrated environment, including the accelerator. CAPI Snap plays a role in both. In development, CAPI Snap makes it easy to port program code into an action on the FPGA. The infrastructure takes care of the common tasks so the developer can focus on the algorithm and data manipulation. On the host side, The API is simple to integrate the application with the accelerator. In deployment, CAPI Snap's infrastructure manages the jobs, handles multi-application virtualization and address translations, and moves all of the data on behalf of the application's acceleration request. This table takes a closer look at CAPI and CAPI Snap's effect on the development and deployment environments. The hardware requirements row points out that we need very few servers for accelerator development. These servers can be on-prem or in a cloud such as SuperVessel or Nimbix. Conversely, when deployed, there may be many instances of the application and accelerators within a single customer environment, across many customers, and in cloud containers. To these end customers, though, they are likely not aware of the fact that there is an accelerator in the system. They just know that they're getting the best price performance for their application. The CAPI row shows how the virtualization makes it easy for developers by utilizing the same addresses that the application sees. In deployment, CAPI manages all of the virtualization and removes the device driver from the stack. And of ultimate importance in the data centers, CAPI provides security from accelerators bringing down the server and from rogue actors using the accelerator to get at other people's data. As we've been discussing, the CAPI Snap row points to the ease of creating an accelerated solution via the focus on actions and the simple API. And in deployment, CAPI Snap handles the job management and the data movement.
So hello, my name is Bruno Mesnay, I'm from the CAPI team and working on enablement. This is a tool for software guys. So it's not anymore for hardware, very specific skills. You don't need any hardware skills today, you just can play with it. No time to set up an environment. This is already embedded in it, and the time you take is not to set up an environment but to code, to develop your code and optimize it.
Most of the rest of our education series will focus on the CAPI Snap development process. So a final look at the advantages of CAPI Snap versus the old model of PCIe attached accelerators. In the old method, you have the application and the accelerator in your server stack. In order to call the accelerator in the old model, the application must call the accelerator via a PCIe device driver, which entails many non-coherent copies of the data and a long code sequence. Then the data must traverse the PCIe transport layer and full PCIe stack on the FPGA side. On top of that, there are data movers for the host side as well as for any data coming from other IP on or off the card. And with all of this, the user does not get security or virtualization features. On the CAPI Snap deployment side, we still have the application and the accelerator, but the rest of the stack is the shared and open source CAPI Snap code, managing the jobs, the data movement, and the direct access to and from the FPGA. The CAPI Snap framework consists of both hardware and software components. Starting from the host side on the left, we have the application, which links to the CAPI Snap library. On the FPGA side, we have the Snap infrastructure and one or more Snap actions. These are compiled together onto an FPGA card, such as the Alpha data card pictured here. Moving further to the right on the slide, we have external components such as networks and storage, which can be attached via the SFP plus cages on the FPGA card. During the development phase, the application architects decide what actions will be accelerated. That is, functions that will become actions on the FPGA. Any given action may have source data, which is the input data to the accelerated action. For example, if the action were a compression engine, the source data would be the blocks of data that will be compressed. Similarly, the application may define a destination for placing the results of the action upon completion. When the action completes, the SNAP framework informs the application that the accelerated function completed. For example, in this diagram, the source could be a storage location at a SAN address, and the destination might be host memory. A use case for this is a decrypt action, where encryption-protected data at rest in storage gets decrypted on its way to host memory.
So the application writer is going to decide, here's the algorithm that I want to offload. And that's going to be the first step in the prep phase, is decide, what do I want to offload? And in many cases, that algorithm that we're offloading, that we're going to call an action, it's going to have a source of data. That data that you want to work on is residing somewhere. It could be out in memory, in host memory. It could be out on the web somewhere. It could be a Twitter database. It could be in the storage area network. It could be on NVMe on a flash array on the card. That's your source data. And then once the action completes, you want to put your results away somewhere. And that's your destination location. So you have an action, a source of the data, and a destination. And those are the three key parameters that the application is going to need to call the SNAP library. What action am I doing? Where's my source data coming from? And where do I put my results?
The power of the CAPI SNAP API is in the flexibility to mix and match source and destination pointers. There can be any combination of host memory, flash, storage, Ethernet, on-card DRAM, or other featured locations. The source and destination pointers can also have multiple data locations. So if you wanted to accelerate a database operation, such as a join or intersection, CAPI SNAP's API allows you to have multiple source pointers to designate data from many locations. The CAPI SNAP framework is divided across the application and host library running on the Power Core and the accelerated action running on the FPGA. Let's look at all of the components. The first pieces to highlight are the base CAPI modules, shown in pink. On the host side, we have the operating system enablement components of libcxl and cxl. These libraries have been uploaded to all of the major Linux distributions, including Red Hat, Ubuntu, and SUSE. These libraries allow the Power Server core to communicate directly to the FPGA's power service layer without going through the heavyweight PCIe device driver. The power service layer, or PSL for short, resides on the FPGA. It communicates directly with the core and manages caching, security, and virtualization on behalf of the accelerator. Next is the CAPI SNAP infrastructure. On the host side library, we have the job queue and controls that interface with the application and call the CAPI libcxl. On the FPGA side, the SNAP infrastructure contains the local controls and job queue, the MMIO engines, and all of the data movers. The infrastructure talks directly to the PSL, thereby hiding from the programmer the complexity of the PSL's cycle-by-cycle computer-engineered interface specification. We use industry-standard AXI interfaces to communicate between the FPGA components and the accelerated action. The AXI bridges are card dependent based on the contents of the card. It might have an NVMe on the card, or it might have SFP plus cages for fiber channel or for Ethernet. Many cards have gigabytes of DRAM, and we have an AXI bridge for that as well. The final components are the application code on the host and the accelerated action on the FPGA. Shown in yellow, these are personalized algorithms written by the developer. The accelerated action fits in the center of all the FPGA components, surrounded by AXI bridges that deliver the application's job request and the data from the many potential sources. The action code can be written in C or C++, VHDL, Verilog, or other languages supported by the FPGA tools. On the host side, the application will use a function call to request the accelerated action.
So the question was, as you have multiple applications calling for one or more actions simultaneously, how does it schedule? So today's CAPI snap is going to do first come first serve on the action, but we can add to that the capability to prioritize if you wanted to have priority. I mean, it's all right in the job queue section, and because this is open source, if you had a special use case, you could grab that and change it. As you get to multiple actions running simultaneously, if the first action had a queue of 3 or 4, you come in with a request for the second action, that's got its own queue. So it's not going to wait behind the other 3 to do that. Okay.
During compile time, highlighted by the red arrows, the application links to the CAPI snap library, which pulls in the libcxl and CXL libraries. Similarly, the action code and CAPI snap FPGA components go through Xilinx's Vivado compiler to make a runnable image on the FPGA. To call the action, the application will specify the action, the source data, and the destination location, all in a programming structure. The structure contains locations for the specification of parameters and for other potential requirements, such as return codes. Source and destination addresses have similar structures. They have an address pointer, a data block size, a flag to say whether this is source or destination data, and the location type of the data, either host memory, NVMe, on-card DRAM, a storage address, etc.